Welcome to the lecture videos on Chapter 12, which have to do with the laws of thermodynamics. We're going to get to the second law of thermodynamics and how that has to do with entropy, which is one of the more misunderstood things in physics that's commonly known but commonly not well understood. And we'll also talk about the first law of thermodynamics, which has to do with how the different forms of energy, in terms of changing internal energy, work, and heat relate to each other. Because so far we've only talked about heat going into internal energy. And what we want to talk about is how some work can also go directly into internal energy. Now, that type of work is referred to as PV, or pressure volume work, and we'll talk about how you can see it on different types of diagrams that'll be useful, which plot the pressure versus the volume of a substance. Now, solids and liquids don't have very significant amount of volume changes. So since now we're going to look at cases where volume is changing, we're going to focus primarily, almost exclusively, on ideal gases. So most of the results in this case will depend on it being an ideal gas. There are some cases where it does not depend. You can work generally for gases, and I'll try to be clear where it is and where not, but most cases it'll be an ideal gas. Now, we'll talk about cases where you have another way of changing the internal energy, not just due to heat, but due to work. That'll change our heat capacity in our specific heats. Because if you have a way of putting energy into your system to change the temperature other than heat, now the amount of heat you need to go, say, increase the temperature by 1 degree Celsius will change depending on how much work goes on. And it'll depend on the process, how you get from some initial pressure, volume, temperature, etc., to your final volume, temperature, pressure, etc. And so therefore we're going to start introducing specific processes, specific ways that you get from the beginning state to the end state, that will be simplified, where some variable is zero or something is not changing. And they're going to be an isothermal process, an isobaric, an isovolumetric, and adiabatic, which respectively mean that the temperature stays the same, the pressure stays the same, the volume stays the same, and there's no heat transferred in this process. These will be good approximations for many cases, but those are just 4 out of an infinite number of ways to go from your initial state to your final state. So don't think of it as an exhaustive study of what happens as gases change. Once we understand how you get work to show up in the different types of processes, then we can start to put it into good use. We can start talking about the machines that take advantage of this, which are very handy in day-to-day life, which is heat engines and heat pumps. Heat engines are how you can use heat, specifically say like you're burning something like gasoline or coal, and you then use a gas's motion and expansion and contraction, heating and cooling it, in order to push and produce some work on an object. So, for example, make your car drive. So that is to understand how that works, we'll have to talk about heat engines. Heat pumps are most familiar in everyday experience as refrigerators, which make things colder. So we'll talk about how you can do that, and we'll also talk a little bit about how they have a second function, which is as a heating device, actually. And we'll talk about how it works in that case. Now, in order to describe it, we're going to talk about the most efficient version of them, which is called the Carnot engine, for the most efficient heat engine. And we'll talk about what do we mean by efficiency. How well did these machines work, and what sort of limits do we have on them? What's the best we can ever do with these types of engines? That to help us understand where that limit comes from, we'll talking about entropy and the second law of thermodynamics. And the second law of thermodynamics says that the total entropy of the universe must stay constant or increase over time. So we'll talk about what is entropy, and we'll talk about it from 2 different ways. Entropy from the thermodynamic point of view, which is to say, how does entropy relate to things like pressure and temperature and volume and all those variables that we've talked about so far. And from a statistical mechanics point of view, which is to say, what really is entropy fundamentally, and why is it that it's something that should increase over time.